So we're talking about mechanisms and rate determining steps. So let's look at this energy diagram. This is just to help us visualize what's going on. So here we have energy increasing as you go up on the y-axis, and this is reaction progress. So that might be related to time. We're starting with reactants here and ending with products over here. The products are lower in energy than the reactants. So is this an exothermic or an endothermic reaction? It's exothermic, because the energy, this delta H reaction here, the energy that's lost as chemical potential energy has gone into the surroundings, and that's why the products have lower energy. So in Chem 1A, we didn't worry about what happened in between the reactants and the products, but we're more advanced now, so we can think about this. So this is an energy diagram for a two-step mechanism. So we have one step, the reactants react, and there's an intermediate that's formed right here. There's an activation with that step of the reaction, and that's this right here. You get here, and then there's another step, which also has an activation energy, and then you go to the products. This activation energy is smaller significantly than this activation energy. And what we've learned by looking at the Arrhenius equation is that when the activation energy is large, the rate constant is small and the rate is slower. So this first step is going to be the slow reaction. That's going to limit the rate of the whole thing, because once you get past this hump, everything goes. It'll just keep going. But this is the slow point. So at the top, where we have these activation energies, these are known as transition states. And we may or may not be able to identify what the transition states are. We may or may not care what they are, but this is a transition state. And what happens is the reactants approach the reaction, and they may begin to form that transition state, but if they don't have quite enough energy to do that, then they'll just go back to what they were doing. We talked about that frequency factor with that weird molecule that was switching the carbon and the nitrogen as if it was wagging. And so it's going back and forth, and each wag is approaching making this. And if we have enough energy to get to this point, then it'll keep going. And otherwise it'll go back. So in this one, the first step is determining the overall rate, and it will predict the same rate law as the experimental data does for the overall reaction. Any questions? So conditions for a valid mechanism. So these are kind of the rules. The elementary steps in the mechanisms must sum to the overall reaction. So if you make up a mechanism and when you add all the steps together, it doesn't give you the overall reaction, something's wrong. I'm trying to dim the lights and I'm pressing the wrong button as I'm saying something's wrong. Okay, the second condition is the rate law predicted by the mechanism has to be consistent with the experimentally observed rate law. Like other things, we can't prove things to be true. We can't prove mechanisms to be true. We can validate them. We can say this meets the conditions. We have no evidence to show that this is not the correct mechanisms, but we can't prove a mechanism to be correct. Other mechanisms might also fill those conditions, and so we might have two mechanisms that look equally valid. And we may or may not be able to do more experimentation to figure out which is the correct one. Okay? So we're going to look at a couple of different possibilities with these mechanisms. So if you have a mechanism where the first step is the fast one, fast initial step, then the rate law that's predicted by the rate limiting step, which is going to be the second or third or whatever, that may contain reaction intermediates. The second reaction might depend on the concentration of an intermediate. But if we come up with a rate law for that, it can't correspond to an experimental rate law. Any ideas why? Well, let's make up something. So let's say that we have A plus 2B, and our first step here is that, well, let's do the overall first. This is dumb, but that's all I can think of right now. So if that's our overall reaction, we could think of, well, this might be an intermediate, a first step. Oh, that one's not even balanced. There we go. We could imagine that, well, maybe the first step is A picking up one of the B's and being AB. And then the second step might be that that intermediate picks up another B and becomes AB2. Okay, very, very simple, but possible. So if this is the if this is the slow step, because the first step is fast, then the reaction mechanism is going to depend on the second step. The rate law for that would be rate equals K times the concentration of AB times the concentration of B. For individual mechanism steps, they're called elementary steps, we can determine the rate law from the chemical equation, only for elementary steps. We can't do that for the overall reaction, okay? So this would be the rate law from this elementary step. Could this possibly be the rate law for the overall reaction? If we didn't know what this rate law was and we were just writing it with, say, n's and m's for exponents, we'd say that the rate equals K, and it'll be each of the reactant concentrations, right? It'll be A to some exponent, we don't know what it is, times the concentration of B to some other exponent. Is AB in there? No, because AB isn't one of the reactants. AB is an intermediate. It gets formed and then it gets destroyed. And so it doesn't show up as a reactant or a product. When the first step is fast, we'll label these. Get rid of this. Oh, that's not what I meant to do. Get rid of this. We're saying that this one's fast and this one's slow. First step happens really fast. The second step is slow. That's going to determine the rate.
Intermediate is something that is formed and destroyed?
Yes. An intermediate is formed during the reaction and then continues to react and form something else. In a way, a catalyst and an intermediate are sort of opposites. Catalysts are there to begin with. They participate and then they get reformed. Intermediates are not there to start with. They get formed and destroyed. So they don't show up in the end. So they're kind of opposite. So if this is the fast step and this is the slow step is going to determine the rate. The rate law for that slow step may not be exactly the same as the rate law for the overall reaction because this has an intermediate in it. There's no combination of exponents that we can use to make this into this, right? I got a couple of nodding heads. Does that make sense? Okay. So that's why a rate law containing intermediates cannot correspond to an experimental rate law because the experimental rate law only has reactants in it. It never has intermediates. So how do we deal with that? Well, we understand that when the first step is fast enough, we may get an equilibrium established between the reactants and the products of that fast step. And that will allow us to relate the concentration of AB to the concentrations of the reactants. And I hope there's more on the next slide. Oh, good. It's like I don't want to come up with a whole example for this. Okay, so this is an example of a mechanism with a fast initial step. So this is our overall reaction, 2H2 plus 2NO forming 2H2O plus N2. This is our observed rate law. We've learned how to figure those out. We look at experimental data, we compare, well, if I change this concentration, how does that affect the rate? And that's how we get those exponents. Everybody, remember we were doing that? Even if you don't remember exactly how to do it? Now we're adding to this and we're saying, okay, this is the mechanism for this reaction. The first step is fast, the second step is slow, and then the third step is fast. We could check and add all these equations together, and those should give us our overall equation. So it says, show condition 1 is met. Elementary steps add to overall reaction. Okay, well, I guess we're supposed to do that then. I write these slides and then I just come back and do what they say. How do we do that? We're going to add both equations, so we need to keep our arrow kind of lined up. And so we're going to look at all of these things as reactants. We're going to add them together and put them over here. And we're going to look at all of these and put them as products and add them over there. And then if we have a term that appears on both sides, we can kind of cross it out. So we can either cross out, they're like spectator ions. We can either cross out terms that disappear in the individual steps or when we finish the equation. Which would you rather do? Cross it out while we're adding it? Okay, so here I've got 2NO. Does that appear anywhere else? No, it doesn't. No, huh? My favorite molecule, besides caffeine. So I'm going to write that one down because that's not canceling out. Let's look at this one. H2. Are there other H2s? There's one here, but none on the other side. So I'm going to take these two and put them together. I have two of them, so 2H2. And I'm going to maybe just draw a line through these so that I remember that I've taken care of those. N2O2. Okay, there's an N2O2 over here. So this is something that's being created and then destroyed. So we're not going to include that in our overall reaction. And we've got N2O, and we also have N2O over here. So that's another thing that's being created and then destroyed. So we're going to cross that off. So I got through all my reactants, so that's good. And now I'm going to look at products. So I've got H2O, and here's H2O. I've got two of those. So I'll write that down, 2H2O, and it's a gas. So I've taken care of those guys. And then the last thing is N2, and there's nothing for it to cancel out with. The order of the reactants is different, but other than that, that's identical to the overall reaction. Everybody okay with that? So condition 2 for an acceptable mechanism is that the rate law predicted by the mechanism is consistent with the observed rate law. So let me just double check here. So what we're seeing here in this slide is the first step and the second step. The first step is fast. The second step of the mechanism is slow. The slow step is going to be rate determining, right? So do we care about the third step? No, that's not going to affect the rate. What is the rate law for this slow step? For elementary steps, we can predict the rate law. The rate will equal K times the concentration of H2O times the concentration of N2O. So here's the rate law in terms of that slow step. Okay, so it's H2 and N2O2. It's the reactants, not the products. I don't know what I was thinking earlier. So in order for this mechanism to be good, the rate law predicted by the slow step has to match up with the experimentally determined one. Well, this one doesn't because it has an intermediate. Which of these is the intermediate? N2O2. So this is the intermediate. We need to figure out, could we get rid of that somehow? Could we substitute something else in? Well, is there a relationship between these two concentrations? It's an equilibrium, right? So what did we learn about equilibrium constants way, way long ago? The equilibrium constant for that is going to be the product concentrations divided by the reactant concentrations raised to the power of the coefficient. So this is actually I'm going to write it up here. That'll make more sense. So for this first reaction that's in equilibrium, we can say that the equilibrium constant is equal to N2O2 divided by NO squared. You okay with that? So then we can take this equilibrium expression and we can solve that for N2O2. I didn't really leave myself any room for that. So I'm going to take that and I'm going to do it over here. So if I want N2O2 by itself, N2O2 is equal to the equilibrium constant times NO squared. Yeah? In this equation, I'm just multiplying both sides by NO squared, and I get N2O2 equals K times NO squared. Everybody on board with that? So I don't want this N2O2 in my rate law because it's an intermediate and I have no way of knowing what the concentration is. But the concentration of that intermediate is equal to this thing. So I can substitute that into my rate law. So rate equals the rate constant times the hydrogen concentration times the equilibrium constant times NO squared. This is better, right? What are we going to do with the equilibrium constant? We can lump that in with the rate constant. Just put them together. We don't know what this number is right now anyway, right? This is some constant, and so it can just be in here. So we can lump the constants together and come up with the rate is equal to a constant times H2 times NO squared. I know some of that seems a little bit like voodoo. You would only do that with intermediates. So what happens is we look at the slow step. This is when the first step is fast. That's when we can run into intermediates. We look at the slow step. We can determine the rate law for the slow step, and then we can use equilibrium relationships to get rid of the concentration of that intermediate. So now, does this match? Why, yes, it does. Right? It's the same as that one. Any questions? Okay, let's do an example. Ozone naturally decomposes to oxygen by this reaction. The experimentally determined rate law for this reaction is given there. Show that this proposed mechanism is consistent with the experimentally observed rate law. Well, what's the first condition that needs to be met? The individual steps have to add up to what? The overall. So let's check that first. Go down here. We're going to add these together and make sure that we can get this equation out of it. So I'm just going to start with the first reactant is O3, and there aren't any O3s over there, but there's another one here. So I've got two O3s. And then I've got, as another reactant, I have just an atom of O. And I'm going to check on the other side, and oh, there's an atom of O. So the oxygen atom gets formed, and then it gets combined with other stuff and goes away. So now I've gone through all my reactants. I'm going to look at my products that I have left. I have O2, and I have 2 O2, and I believe that would be 3 O2. So condition 1 is met. The individual steps add up to the overall reaction. The second one is that the rate predicted by the mechanism has to match up with the experimentally determined rate law. So what we have here is we have a fast initial reaction and a slow second reaction. The slow reaction is going to determine the rate, okay? So we can look at this elementary step and identify what the rate law for the slow step would be. So the rate law for the slow step. Rate equals constant, and then we're looking at the reactants. The reactants are O3 and O. And neither of those in this slow step have a coefficient. Their coefficient is 1, and so the exponent is 1. So if I lose you at any point, let me know so we can find you and before we keep going. Everybody okay? So in order for this to be a valid mechanism, which is what we're trying to show, this rate law has to agree with this one. Well, those aren't the same. This has an intermediate in it, right? And this rate law doesn't. So what we need to do is we need to substitute in something else for that, right? Well, what can we do? We can look at this first rate here and identify the equilibrium expression for that. See what happens here, this reaction is fast, and most reactions can go in both directions. It's just sometimes they don't, but they can. This reaction's fast, the next one is slow. So this is making oxygen atoms, but the next reaction's really slow. So instead of going forward, these are going to go backwards. And this is just going to go around and around. It's going to establish an equilibrium. And this second step will draw from the equilibrium. So the equilibrium constant for that reaction is equal to the concentrations of the products, O2 and O. There aren't any coefficients. Coefficients are 1, so the powers are 1, the exponents, divided by the concentration of the reactants raised to the exponent corresponding to their coefficient. And then what I want to do is I want to take this equilibrium expression and rearrange it so that it says O equals something. Concentration of O equals something in terms of that, right? So what I'm going to do is I'm going to multiply both sides by O3, and I'm going to divide by O2. So I'm going to end up with the concentration of O is equal to the rate constant times O3 divided by O2. Everybody okay with that? I can take this and substitute it in for O. So I'm going to write rate equals K times O3. And we've got colors, let's make use of them. So this part, I'm substituting in K O3 over O2. That's a big K, that's a little k. They're both constants though. Yes? How did I switch this around?
Yeah.
So I wanted O by itself. So I've got K over here, I'm going to multiply by what's in the denominator, and then I'm going to divide by what's in the numerator. Okay? We do a lot of this sort of rearranging, and so this is how I think of it. So if you think of your equation or your proportions, you've got a top and bottom on both sides. I can take anything from the top here and stick it in the bottom over there. You can travel diagonally across the equal sign. So I can put this in the bottom, and I can put this in the top. And if you learn to think of the equation that way, you can rearrange it very quickly. I can prove to you why that works, but that just is a lot faster. Any other questions? So I rearranged this, I solved for O, concentration of O, and then I plugged this in where O was. Then I need to look and see, well, can that be simplified in any way? Well, yeah, we should combine like terms. We're going to combine the constants. So rate equals rate constant. I've got O3 squared. And I'm kind of keeping my eye over here on this experimentally determined rate law. This is showing it as O2 to the negative 1. Well, this is O2 in the denominator, and so that is O2 to the negative 1. And it's probably written that way because it's easier to look at that and say, oh, the order for O2 is negative 1. We haven't seen a negative rate order before. There's lots of things that exist that we haven't seen. So the slow step does predict the same rate law that the experimentally determined one is. Neat, yeah.
So if it doesn't say fast or slow on the side of it, how do we determine which is the
That's an excellent question. If it doesn't say fast or slow, then what do we do? I don't know if we're going to do that to you. If we're going to do that to you, it'll show up in the next few slides. I can't remember. But yeah, there's no way you'd be able to know just by looking at it what it is.
So is the first step always going to be equilibrium?
If the first step is fast and the second step or one of the other steps is slow, then we usually assume equilibrium. If the first step is slow, though, then we don't have to worry about it because we won't end up with intermediates in our rate law.
Okay.
Any other questions? Yeah.
How did you know to plug all of that in for O?
How did I know to do that? Well, I've learned how to do these problems. So I'm trying to teach you a method for getting rid of this intermediate concentration. And so this is a common thing we do in math when we're proving things or just rearranging stuff. If I don't like what this is, if I can find something else that is equal to it, then I can substitute, because here I proved that this concentration of O is equal to this thing. And so instead of writing that, I can write this because they are the same. And I wanted to do that because this has reactant and product concentrations which show up here and thus could be measured. I don't want an intermediate concentration because that's forming and getting used up and I can't measure it. Does that help?
Yeah.
Any other questions? You'll have to do something like this on the exam next week. One more question?
Yeah. When you wrote the part with all the red on it, how did you write all of that? Like, I know how you switched it, but how did you write?
Okay, so that goes back to equilibrium, which is also a review from Chem 1A. So, or 3A. So let's look at how that happens. So I'm going to write our generic equation again. AA plus B, here we're going to make this an equilibrium. CC plus D. And then I can write the equilibrium constant. That's going to be equal to the concentration of the first product to where the exponent is the coefficient. Concentration of the second product, exponent is the coefficient, divided by the reactants, where their exponents are their coefficients. Okay, did I come back now?
Yeah.
So that's the definition of an equilibrium constant. Now, just a couple tricky things about that. If you have a solid or a liquid in your equation, do we put those in the rate constant? No, we don't. Because the concentration of a solid or a pure liquid can't change. And so we leave them out because we all decided to do that. Okay? The concentrations here always have to be in moles per liter. The rate constant then would have all kinds of different funky units. And so we all agreed to say, we're just going to drop all the units for the rate constant because it's just ugly and pointless. Okay? Any other questions? You might ask, well, why don't we do that for the rate constant? Because those units are weird too. I don't know, but we don't. Okay. Predict the overall reaction and rate law that results from the following two-step mechanism. Simple mechanism here. The relative rates here are given. The first step is slow, the second step is fast. So first, let's predict the overall reaction. We do that just by adding the two equations, right? So as I add these, over here I have 2A, and I don't have any other, just plain A's. So 2A. And another reactant is A2, but there's an A2 on the other side. So I'm going to cross those guys off.
Can you have more than one intermediate?
You can have more than one intermediate.
And then you have to do all of the intermediates?
Well, if you're determining a rate law from an elementary step, usually that elementary step only has one intermediate in it.
Just
And
the elementary stuff.
yeah, when you're doing what we just learned how to do, you're looking at the slow step, and you only have to do that if you have a fast step first. So the A2s went away. The other reactant I have here is B, and so we have to include that. So I've got these down, this one down there and that one down there, and then the only thing that's left is this A2B. So that's our predicted overall reaction. Everybody okay with that? Now we're supposed to predict the rate law. We're doing this from the elementary steps. Are we going to look at the slow step or the fast step? The slow step. So the rate law for the slow step, rate equals K. So sometimes when students are instructed to write the rate law, they just write K times this times this times this. The rate law is the rate equals something. So rate equals K, and then what are we going to do? I'm going to erase all of my scribblings here. This is an elementary step. We can predict the rate law for the elementary step from the equation. There's only one reactant, right? Concentration of A. And what's the order? 2. 2 A's are reacting to form A2. And so this is a bimolecular step, and it's A squared. Do we need to substitute stuff in and get rid of something and look at equilibrium constants? Nope. This is the rate law predicted by the slow step. The slow step here is first. We don't care what comes after it. So this is the predicted rate law for this overall reaction. So what's the order for B? 0. It apparently doesn't depend on the concentration of B, just on the concentration of A. But it's second order for A. Any questions?